Hello, everybody. In Module 1, I provide introduction to theory, discuss traditional models of capital markets, and explore how disclosure affects various capital market outcomes. Module 1 has 6 lessons. Today, we're going to talk about Lesson 2, Basic Math Tools. Recall from Lesson 1 that a model has both exogenous and endogenous components, and it's very important to differentiate between those two types of components. One reason is that the math tools dealing with those components are going to be different. Let's first look at exogenous components. Exogenous components, they are not choices of any players of the model. They're usually some exogenous states of nature. For example, future macroeconomic conditions could be good or bad. Nobody chooses it. Tomorrow's weather will be rainy or sunny. Nobody chooses it. Usually, investors are uncertain about exogenous components, but they have some prior beliefs about the distributions of those components. Subsequently, when they obtain information, they're going to update their beliefs about the distributions of those components. This is what we call the posterior beliefs. It's formed using Bayes' rule. Now let's use some examples to illustrate. Suppose the future cash flow of a project denoted by theta is either big H or big L. Theta is exogenous. Investors cannot observe whether theta is big H or big L, but they perceive theta is H with probability Q for some number Q. Subsequently, investors, they obtain some information, let's say earnings information about theta. They know this earnings information as X, which can be small h or small l. In this setting, assume that conditional theta equals big H, the probability of X being small h is the same as conditional theta equals big L, X being small l, to be some number t that is between 1/2 and 1. After observing those future cash flows, investors are going to form posterior beliefs about theta using Bayes' rule. This slide provides a step-by-step derivation of how to apply Bayes' rule. I'm not going to go through the algebra, but eventually we're going to calculate the posterior distribution of theta being big H, conditional X being small h. This probability is going to be bigger than the prior probability of theta is big H. The reason is conditional theta equals big H. We're more likely to see X being small h than small l. So upon observing X being small h, we're more optimistic relative to the prior that theta is going to be big H. So that's why the posterior probability is higher than the prior. The number t captures the informativeness of X about theta. The higher t is, the more informative X is about theta. So for higher t, when we observe X is small h, we're more confident that theta is going to be big H. So the posterior probability is going to increase with t. Now let's look at another example. Suppose future cash flow of a project is not binary, but continuously distributed. The prior distribution is normal with mean mu and variance 1 over alpha, or equivalently, precision alpha. And suppose investors, they obtain some information about theta. Let's say this is earnings information. X is theta plus eta. Eta is also a normally distributed random variable with mean 0 and precision beta. And eta is independent of theta. Once investors observe X, they're going to form a posterior belief about theta. This Bayesian updating process can be quite daunting, but the results are actually pretty simple. The posterior distribution of theta is still normal. The mean is the weighted average of the prior mean and the realization of X, and the weight is given by the precision. And the precision of the posterior distribution is the precision of the prior distribution and the precision of X conditional on theta, alpha plus beta. The result is also very intuitive. The higher X is, the higher the expected value of theta is. The reason is because when X is higher, it's more likely X comes from a distribution with high theta. So in this case, investors are more optimistic about the posterior distribution of theta. The higher beta is, the more informative X is about theta. And so investors are more confident about their posterior distribution, or equivalently, posterior distribution is more precise. This is just a simple example. More complicated Bayesian updating, I recommend a classical textbook, the Group 1970, Optimal Statistical Decisions. Now let's look at endogenous variables. By definition, endogenous variables, endogenous components, are chosen by the players. And therefore, it's not a random variable, which means that you cannot perceive them to have some distribution. Instead, you have to form a conjecture about what actions they're going to choose. That also means that any noisy observations about endogenous components has no information content. You're not going to use Bayes' rule. Any discrepancy between the noisy observations about endogenous components and your conjecture, you're going to attribute that to measurement noise. Another tricky thing about endogenous components is endogenous components are chosen by some players. And when those players are choosing those endogenous components, you have to be aware in your payoff function, what is the actual components you're choosing? What is the conjecture? When you're choosing the actions, it can only affect the actions you're choosing. It will not affect the conjectured actions you're choosing. And those conjectures are not arbitrarily chosen. It has to be rational. What it means is that in equilibrium, the conjectured actions have to be the same as the actual action. So those may be too abstract. Now let's use an earnings management example to illustrate that. Suppose a manager privately observes true earnings and privately chooses some reporting bias. And choosing reporting bias is costly. Think about this as earnings management cost. Investors do not observe theta. They form a prior distribution of theta. And they can also not observe reporting bias. Instead, they observe the sum of theta and reporting bias with some noise. The investors, they're going to set price to be the expected value of theta conditional on the noisy observation of the report they have and their conjecture about the manager's misreporting. Because misreporting is the endogenous variable. And so you don't do Bayesian updating, you form conjecture. And the manager's objective is to maximize the expected price minus the manipulation cost. And we're going to see that in this price, there are going to be components of manager's actual choices. There are going to be components of conjecture. The manager's actions can only affect its actual actions. The conjecture must be held fixed. And in this case, because noisy observation of endogenous components has no information content, the market is not going to use Bayes' rule to update manager's misreporting choice. They're going to set price equals to X minus some conjecture about manager's manipulation, because manipulation choices is endogenous. And so in this case, from the manager's perspective, expected value of P conditional on theta and A would be expected value of X, but expected value of X is expected value of R. And R is theta plus A theta. So this R is determined by manager's actual choice. But the minus A hat theta part, minus the conjecture part, that is not controlled by the manager. That's just the market's conjecture. So when manager is choosing A theta to maximize the objective function, the manager has to take A hat as fixed. Only the A theta part, that is affected by the manager's choice. And the first order condition is going to give you A theta is 1 over C. And in equilibrium, the conjecture has to be reasonable, which means the conjecture has to be the same as the equilibrium choice. So A hat theta is going to be 1 over C as well. So this shows you how to solve a problem with endogenous actions. The takeaway for lesson 2 is that for exogenous components, the math tool is Bayes' rule. Use Bayes' rule to update. For endogenous components, there's no Bayesian updating. You have to conjecture the endogenous components. And in equilibrium, the conjecture is not arbitrary. They have to be consistent with the actual choice. But when you're making the actual choice, you have to take the conjectures as given. So that's all about lesson 2. Next lesson, we're going to discuss the Grossman-Stiglitz model, which is one of the workhorse models in information economics and information-based capital market trading. The key takeaway is that prices aggregates information and thus is informed. If you want to check your understanding of the materials for this lesson, a review quiz can be found at the link in the slides. Thank you very much.